All right, so let's move on. The next topic we're going to discuss is average rates of change. Now, to be honest with you, you already know what an average rate of change is, except you're not used to hearing it called by this phrase. Remember linear functions, linear equations, they have this thing called slope, right? We remember it as rise over run. In other words, how high and how far across is this thing running, correct? All right. Well, that's only for a linear function. If I have a graph that's not linear, such as this one over here, I can't find the slope of that curve. However, if I choose a couple of points, let's say this point here, I don't know exactly its coordinates, that's okay. So I'm going to call it A, and then the y value would be f of A, wouldn't it? Because I'd find the y value by plugging in the a to the function, agreed? Okay, and this point here, we're going to call it B, and then, yep, f of B, because that's how I would find its y value, agreed? So if I take these 2 points and I draw a line through these 2 points, then I technically could find the slope, couldn't I? By the way, this line that I've just drawn between these 2 points, this line is known as a secant line. That is technically what that line is called. I know, back to geometry days, right? But that's okay. This is technically called a secant line. So here's the thing. I could still find the slope, but because I'm working with a curve and I had to create the line, and by the way, it was my choice how far apart these points were going to be or how close together they were going to be. That was my choice for this particular example. I can find the average rate of change. Now, I'm going to be honest with you. Sometimes I get a little lazy and instead of saying average rate of change all the time, I call it AROC, which stands for average rate of change. Now remember slope, it's the difference of the y's over the difference of the x's. Agreed? Okay, well, same thing. The difference of the y's over the difference of the x's. Now remember, you have to subtract the x's in the same order you subtracted the y's. So since I put f of a first in the numerator, I'm going to put a first in the denominator. Or you could switch these around. Put the f of b first, which means the b goes first. It doesn't really matter. Cool? Okay, so let's look at an example. Let's say I have this function, x to the third minus 1. And the interval I am going to work off of is the interval from 1 to 3. And I would like to find the average rate of change. So, according to our formula for average rate of change, I need to find, right? I need to know my y's and my x's. Agreed? Well, if I'm on this particular interval, what do you think this represents? The y's or the x's? Some of you said it. Some of you aren't sure. Some of you gave me the wrong answer. So here's the thing. When they give you an interval to work off of, this interval is the domain. And if it's the domain, that means it represents your x's. So I know one of my x's is 1 and my other x is 3. So now I need to find f of 1 and I need to find f of 3. Okay, give you a few moments, go find it and then come back. Did you get them? Okay, so f of 1, yeah, you're going to find it by plugging in the 1 to the f of x, right? So I got 0. Did you? Okay. And then f of 3, same thing. You're going to find it by taking the 3 and plugging it into the f of x function. What'd you get? Yep, I got the same thing. And now I can find AROC. So, to find AROC, this is going to be the difference of the y's. So I'm just going to say 0 minus 26 over the difference of the x's, 1 minus 3. So it looks like I'm getting a negative 26 over a negative 2, so I get 13. Cool? Now, some of you are like, well, that's fine and dandy. What the heck does that mean? Let me show you. All right, I'm going to give myself a little bit more board space over here, so just bear with me. Technically, that is your slope between a couple of points. So if I give myself a graph, and I have 2 points on this graph. I have 1, 0. Sorry, my brain is trying to give myself a little bit more room to work to show you. So I'm moving my x-axis. So 1, 0. And the other point is 326, isn't it? All right, so let's see. All right, let's just say 26 is up here. 326. By the way, just to give myself another point to work with, if I plugged in a 0 here, what would I get? Good, negative 1. Why am I asking for that? Because I literally would like to draw as much as I can, as accurately as I can, the graph of this particular polynomial. This is a third degree polynomial, which means it's got that funky little S shape. But here's the real deal, right? Here's the real reason I'm graphing it, is because technically between these 2 points, since they were only looking on the interval from 1 to 3, and these were the y's that went with these x's, I can draw this secant line. It's a quite steep secant line if you notice. And the slope of that secant line is 13. 13 over 1, which means from here you go up 13 and over 1 and up another 13 over 1, and you keep on going, so to speak, and that would be the average rate of change for that secant line. Good? Cool. So average rate of change is used for non-linear functions. I'll be right back with you. Okay, so we're going to go over a definition that actually uses the average rate of change. That's like our next example. So let's look at the definition. The definition is the definition of what's called the difference quotient. So let's look at it. The average rate of change of f of x, which is a function, with respect to x, that means that x is the variable inside the function, is also called the difference quotient, given by this wonderful little formula, where h, which is in the denominator, can't equal 0. Cool? Like, wait, how'd they get that? Hold on. This part of the definition is quite important. The difference quotient is equal to the slope of the secant line. Remember, when you choose those 2 points on the curve and you draw the line through it, that's called the secant line, right? And so it's passing through 2 points, isn't it? So one of the points would be x, and its y would be f of x, and another point is x plus h. So I went this direction h spaces or that way h spaces, it doesn't matter. And I find its y by plugging in, right, x plus h into the function. So this difference quotient is equal to the slope of the secant line passing through these 2 points. So let me show you what they did. I know the slope formula, right? I know the average rate of change formula, correct? The average rate of change formula is equal to the difference of the y's over, right, the difference of the x's. Agreed? Okay, so if all I do is simplify the denominator, because there's not a whole lot I can do to the numerator, I'm noticing that the x's in the denominator drop out, and I am left with simply having an h on the bottom. So this, right, I used the average rate of change formula, didn't I? So using the average rate of change formula gave me this. But we're calling it the difference quotient. It is a generic formula that will always give me the average rate of change. Always. Cool? Okay, so stay tuned. I've got some examples using the difference. All right, so let's look at this example. They're asking us to find the difference quotient for this particular function. So first off, when they ask me to find the difference quotient, I always write the formula down. Why? Because I want to know what it is I need to work with. So the difference quotient is equal to f of x plus h minus f of x all over h, right? Okay. So we need three things to work with the difference quotient. We need to know f of x plus h, we need to know f of x, and we need to know h. With me? So let's go to the side over here. One of the things we need to do or need to know is f of x plus h. Well, to find f of x plus h, this means take x plus h and plug it into where? Yes, plug it into that function, right? So that means I'm going to have negative 5 and in parentheses x plus h squared. Cool? Okay, we should probably simplify that. So, because I'd rather simplify as much stuff out here before I plug it into the formula. That means we have to take x plus h times itself. And yes, I'm assuming you remember how to distribute these two binomials. All right, so this gives me negative 5x squared. Whoops, not plus because I'm distributing a minus sign, correct? Minus 10xh minus 5h squared. Cool? So here is my f of x plus h. Got it? Okay. The other thing I need to know is f of x. Well, I got f of x. It's right there. And the other thing I need to know is h. Well, h I don't have, so h is just going to stay h. So when I go back to my formula and I start plugging things in, the difference quotient needs to be equal to, or is equal to, f of x plus h, which we found over here, negative 5x squared minus 10xh minus 5h squared minus f of x, which is this negative 5x squared, all over h. Cool? Okay, time to do some simplifying. So I'm going to get rid of the parentheses out of the numerator, which will make life a little bit nicer. This double negative goes to a positive, doesn't it? And I don't know about you, but I'm noticing those 5x squareds are going to cancel. So yay for that. So that leaves me a negative 10xh minus 5h squared all over h. Oh, looky there. I'm noticing some h's are canceling. So my difference quotient here would be negative 10x minus 5h. Woohoo! And you're like, well, that's fine. What does that mean? Hold on. This is a generic formula to find the average rate of change. So, if I knew one of the x's, let's just say the x was 5. H is the distance between that x and the next x. So let's just say h was 2. So I'm going from 5 and I'm going 2 spaces, okay, to get to the next x value. Got it? Okay. The difference quotient would tell me that to find the slope, to find the average rate of change between this x and the x that's 2 spaces down, to find that average rate of change on that secant line, I would simply take negative 10 times 5 minus 5 times 2, which would give me negative 50 minus 10, which tells me that the average rate of change for that secant line between this x value and the x value 2 doors down is negative 60. Got it? This negative 60 is the average rate of change for the secant line from 5 to the next x, which is 2 spaces away. By the way, what would be that x 2 spaces away? Yeah, it would be 7, wouldn't it? So technically I would have 5 for the x, and I have 7 for the other x, wouldn't I? Okay, I'm going to show you a quick check using the average rate of change. So, still using this formula, this function. So if x is 5, and you plug it into this function, what would its y value be? Good, negative 125. Gotcha. If you take 7, and I need to find its y value, and you plug it into this function, what do you get? Did you say negative 245? Because that's 49 times 5, isn't it? Good. And if I was going to find the average rate of change between these 2 points, I would take the difference of the y's minus the difference of the x's. So that's positive. So what's the difference on, what do you get in the numerator? I heard you, 120. What do you get in the denominator? Negative 2. So we get negative 60, which is exactly what we got here. The only difference is this. Average rate of change is very specific. I literally need to know the 2 points. The difference quotient is generic. I can pick any x I want, any h I want, and that will find me the average rate of change for the secant line that passes through this x value and the one in this case 2 doors down, or it could have been 3 doors down or 10 doors down or whatever, so to speak. Cool? This one is generic. It lets me choose any x I want, and h's are however many spaces away I want the next x to be. Cool? Okay, so stay tuned. I'll be right back with another example. All right, so let's look at the second example. We're still finding the difference quotient. So remember, to find the difference quotient, the formula says that we need f of x plus h minus f of x, and the whole thing divided by h. Agreed? Okay. So the first thing we need to find is f of x plus h, don't we? Well, to find f of x plus h, we have got to take x plus h and plug it into the function. So I have 1 minus, and in parentheses, x plus h to the power of 3. Oh dear. All right, I'm going to give myself some space, put the equals to sign here. Why? Because that means you got to write this thing out 3 times and distribute. See? Math builds upon itself. You got to know how to multiply polynomials to do the difference quotient. Go figure that one. All right, so I am going to multiply those last 2. And there it is. And now I have one more distribution to do, don't I? Okay, so good idea to take this slow. So I have x to the 3rd. Oh my goodness gracious, I have to be careful. Like, wait, why'd you stop? Okay, because what answer I get here is technically following a subtraction sign, is it not? So I'm going to put this in brackets so that I remember that eventually I'm going to have to distribute this minus sign to whatever I get here after I do the multiplication. So x to the third, right? Plus 2x squared h plus xh squared plus x squared h. I'm running out of room. I'm going to put it down here. Plus 2xh squared plus h to the power of 3. Okay. Let's collect some like terms. So, still have this bracket. Why? Because I am not ready to distribute that minus sign yet. So x to the third, 2x squared h, and one more x squared h. 1xh squared, and two more of them. And then the h to the power of 3. Okay. Well, that's a little better. And now finally, you get to distribute that negative sign, don't you? And after you distribute the negative sign, here is your f of x plus h. And I know, depending upon the function they give you, some of the work that you're going to have to do prior to plugging it in is a lot of plug and chug. Well, that's what we did. We had to plug this in. We had to just work it on through. This is the part that you have to be careful of. This part's actually easier. Why? Because check it out. When I literally put this in to the difference quotient, f of x plus h was this thing, wasn't it? So 1 minus x to the third minus 3x squared h minus 3xh squared minus h cubed minus the original function. All over h. Good? Okay, so I need to simplify that numerator a little bit more. And in actuality, the part that usually ends up needing the simplification is what's following this minus sign over h. And I'm noticing the ones are going to drop. And I'm noticing x to the thirds are going to drop, which is leaving me with negative 3x squared h minus 3xh squared minus h to the power of 3 all over h. Do you see what happens? Yeah, now the h's drop out. And some of you are going, wait a minute. 3x squared. Hold on to that, wait a minute. Why? Because I need to focus. All right. Some of you are like, hey, wait, the h dropped out in the last problem too. Does that always happen? It's supposed to. What's supposed to happen is when you subtract off the original polynomial, it ends up canceling with something over here in the f of x plus h. And then what remains should cancel the h out in the denominator. And this is my generic difference quotient. I'm not going to do an example, but remember what I said on the last problem. I could now find the average rate of change if they give me one of the x's and the h, which represents how far away the next x is. I could find the average rate of change of that secant line between those 2 points technically. I could, when I find them. Cool? Okay, got one more for you, so stay tuned. All right, let's take a look at this third problem. So, still trying to find the difference quotient, because those are the directions. My difference quotient looks like this in its formula. Remember, you should always write it down, so you always know what it is you're trying to plug in. And the first thing I need is f of x plus h. Well, there's not a lot of work to do with this particular one, because this would be just 2 over x plus h, wouldn't it? And then I'm supposed to subtract the original function. Okay. And then the whole thing is supposed to be divided by h. Well, lovely. So, you're like, well, what do you do here? So technically this is a complex fraction, right? We've dealt with these guys before. In the numerator, you need to find the common denominator, which would just be these two guys multiplied by each other. So 2 times x minus this other 2 times the x plus h all over the common denominator. Right? Now, I'm going to write this divided by h a little bit differently. I'm just going to put divided by h over there and write it like the old-fashioned way with the old-fashioned division symbol. Why? Because it cleans the problem up a little bit, and when you're dealing with complex fractions, you really don't want another denominator. And gratefully, this is the only thing in that denominator, so I don't have to worry about doing anything with it. So now, let's look. I'm going to bring this up over here because I have more room. So my difference quotient is looking like 2x minus 2x minus 2h over x times x plus h, and still divided by h, right? And when I simplify the numerator, it looks like I have a negative 2h over x times x plus h, still divided by h. Okay, so remind me, how do I divide fractions? Very good. You multiply by the reciprocal. And I showed that in another lecture somewhere. So if you want to go find it, be my guest. But there's a reason why we multiply by the reciprocal. I promise we didn't pull it out of the thin blue air. Okay, which means in this particular case, this h is going to cancel with that h, isn't it? Which leaves me just a negative 2 on the top and x times the quantity of x plus h on the bottom. And that's about all I can do, isn't it? This original function being a fraction, being a rational function, kind of alludes to the fact that your difference quotient is going to be rational as well. There's no way I'm going to be able to cancel that denominator out. You saw the process. It wasn't going to cancel because I needed a common denominator to multiply these two guys. But that h certainly canceled, didn't it? Cool? Okay, stay tuned. Got a couple of stories. So let's look at this first story. They're asking us to use this graph to find the average rate of change of the percentages of new employees between 1994 and 2000, and then again from 2000 to 2006, and then again from 1994 to 2006, over the entire span, so to speak. Now, here's the deal. Since they want the average rate of change, we need to have x's and y's, don't we? All right, so let's make certain that we read this graph correctly. We are going to first look at 1994, and this is 96, this is 94 over here, which means it's at 0. And we are going to need the year 2000, and that's this double 0, and that's this point right here, which looks like if we go across, it's at 16. And then we need the year 2006, which is this point here, and if we go across, it looks like it's at 20. Now, these are percentages. So let me stick my little percent sign in there because those are the y values, they're in percentages. So we need to find the average rate of change. Now, I don't have enough room on this paper, so I'm going to scoot us to a blank page so we can work. All right, so the first thing they wanted to find was, this is part A, they wanted from 1994, which had 0%, to 2000, which was at 16%. Okay, so to find the average rate of change, yeah, we're going to have to take the difference of the y's minus the difference of the x's. Agreed? All right, so let me get that in there. And they did say round to 2 decimal places as needed. So I have 16 over 6, which is, yeah, this is going to be 2.67. Now, you need to make sure you understand the ending on it. The numerator was a percent. The denominator represented the years. So in this particular case, this is 2.67% per year. That was the increase. Good? Okay. Part B was from 2000, which we already decided was at 16%, and 2006, which was at 20%, is what we saw. All right. Average rate of change. Let's take a look. The difference of the y's minus the difference of the x's. So this looks like what? 4 over 6? Yeah, that's 0.67% change per year, isn't it? Well, it looks like the first 6 years was a larger change than the next 6 years. Just fixing that up a little bit because that really looked weird on my writing, didn't it? Okay. Actually, we're just going to make it even look nicer. I need to make sure you can read this. Okay, now part C. You get the hang of it? You know what you get what we're doing? Okay. So this one wanted to go from 1994 when they started all the way to 2006, which is where they're ending their study, shall I say, their look-see. So the average rate of change is going to be the difference of the y's over the difference of the x's, which looks like 20 over 12, which when you get that decimal is going to be 1.67% change per year. Cool? All right. All right, so the next problem says an object dropped from rest at the top of a tall building on planet X falls a distance of d of t, which equals 14t squared feet in the first t seconds. Well, that's a mouthful. So let's look at that a little bit slower. This formula, right, is representing the distance. So d is the distance, and the distance is in feet. And then the t actually represents, yeah, the t represents time, so distance is in feet. And the t represents time, and the time is in seconds. Okay, so now they want us to find the average rate of change of the distance with respect to the time as it changes from 2 seconds to 10 seconds, right? Okay. This is known as the average velocity or speed. So when we are dealing with distance and dropping things off the top of a building, there is changing average rate to the average velocity. But the formula is still the same, and that's the cool part. So math gives us the formulas and how to use them, and then these other studies, these other areas of studies, take those formulas and use them as they need them for their own purposes, so to speak, and in this case, to find the average velocity. All right, so I'm going to need a little more paper, so I'm going to get us a blank screen. So to find the A rock, I need to know my x's. Well, the first one was 2, And it's not an X, is it? The input was time. So my first time is 2 seconds, and my second time was 10 seconds, and my formula was d of t equals 14t squared, and this was in feet. So if I'm going to find a rock, I need to find my y's for each of these, or the distances for each of these times. So let's find them for each one. And I know you probably have your calculators out. Fine, no problem. So you plug in the 2. What'd you get? Good, I got the same thing. I got 64 feet. You plug in the 10. What'd you get? Good, I got the same thing. I got 1,400 feet. And now I get to plug it into the AROC formula, which is going to be, in this case, the average rate of velocity. So I'm just going to write it that way. Average rate of velocity. Ooh, that word velocity does not look very nice, does it? And regardless, you're still finding it the same way. It's the difference of your outputs, which in this case is going to be 1,400 minus 64, and that's in feet, over the difference of your inputs, which in time in this case, and that's in seconds. I have to make sure that I write the inputs in the same order I wrote the outputs. Okay, so doing your math over there, doing your arithmetic, shall I say, doing your subtraction, your division. When I worked mine out, the numerator was 1336 over 8, still feet over seconds, which actually was very nice. I got 167 feet per second. Did you get the same thing? Okay, good. All right, so hopefully these applications made sense to you. You guys have fun with this section, and I'll catch you on the flip side.